Good morning. Welcome to another webinar hosted by OpenCAD. Today's session is Predictive Maintenance and Industrial Equipment Health Monitoring. And we have a special panelist, James Wiken. He's an application engineer at MathWorks. And James has been working for MathWorks for almost 6 years. And he's an expert in predictive maintenance, among other fields of study. And the session will be presented in English, but we have an OpenCAD data scientist, Daniel Vieira, on staff. So if you feel more comfortable, feel free to ask any question in Portuguese using the question board. Okay? Welcome, James. This page is yours.
All right. Thank you, Sylvia. So like Sylvia said, my name is James Wiken. I'm an application engineer for the MathWorks. And today we're going to be talking about predictive maintenance with MATLAB. All right. So to get started, let's first talk about why we would even want to do this in the first place. All right. So many of you have probably seen, potentially videos or other things where you've seen things like maybe like a wind turbine kind of blowing itself apart as it spins out of control, or any other devices having some sort of catastrophic failure, right? And there's problems with that, right? One, the failure isn't great because stuff will break apart. It costs a lot of money. It potentially harms people, and in many cases for some of these systems, not only is it expensive for them to fail, but it's also really expensive and dangerous to actually do the maintenance to prevent them from failing. So in the case of, say, a wind turbine like this, you would need either a crane like we see here, or a cherry picker, or in more remote locations, you might actually need to fly them in on a helicopter and drop them off on top of the device, right? So all these things are something that you don't want to do all the time, but is necessary to prevent those more catastrophic failures from happening. Okay, so why do we want to perform predictive maintenance? Well, we want to minimize the cost and the risk associated with both of these things, both the operation as well as the maintenance of these sorts of systems. Okay, now it doesn't have to be something big like this or have some sort of catastrophic failure to have benefit from doing this sort of work. And honestly, we do maintenance of various forms on almost any sort of system or device that we use. The maintenance that we can do is something like something reactive, so we're only going to fix it or replace it once there's a problem. Things like a car's battery or maybe a light bulb would be good examples of this. You can also do things like scheduled maintenance, where you have some sort of regular rate that you just do maintenance on, whether it needs it or not. Things like changing your car's oil every 5,000 or 10,000 miles is a good example of that. And while that is useful, it can potentially lead to unnecessary maintenance, which can be wasteful. And there's no guarantee that that rate is actually going to eliminate all failures. I mean, we decide it kind of arbitrarily based on our knowledge of the system and maybe some data we have, but it is just that, just an arbitrary rate. So what we're aiming to do is predictive maintenance, where we're going to build a model so we can forecast when problems are going to arise. That way we know when failure is going to happen, or at least we have a good idea of when it's going to happen, so that we can just do maintenance when it's necessary, as well as also eliminating any failures from actually occurring. Now, big problem with this is that it can be, saying we're just going to predict it is probably oversimplifying the problem, right? It can be difficult to actually make those predictions, especially for more complex equipment. And so we're going to talk about different techniques and tools that we can use today to be able to make that sort of forecast or make those sorts of predictions. Right. Now, at a high level, when we're talking about predictive maintenance, we can be talking about a few different things. And even more generally speaking, predictive maintenance is a form of data science or AI. And in this, what we're trying to do is we're trying to take large volumes of data that we have available to us and try to be able to make decisions based on that data. Okay. Now, in between that, I like to think of either a question or a set of questions we're trying to answer in order to come to a decision. So for predictive maintenance specifically, some standard questions might be, what's the current condition of my machine? And when will my machine fail? The third question that isn't listed here is, why is my machine failing? Might be another one that we might ask, but we're not really going to talk about that part of it today. We're going to talk about these two. Okay, no, the first one, what is the condition of my machine? This falls into a bucket called condition monitoring. Right, so we're going to take sensor data, we're going to monitor it as it comes off the machines in order to be able to identify when changes are occurring, so that we can indicate when a fault is developing or when failure is getting closer to happening. So that's a very, looking at current data to see the current state of the machine. The other one, when will my machine fail? This is where predictive maintenance comes in. Another term for this is something like time to failure or remaining useful life estimation, where we're going to take that same data and we're going to use historical data as well in order to predict or build a predictive model that will tell us when maintenance should be performed. It'll tell us what's the remaining useful life of the system until it fails. Now, I do want to say that failure is something that you define as part of this problem. It doesn't have to be catastrophic. It doesn't have to completely break down or explode or anything like that. It could be something as simple as falling below some sort of efficiency value. So you say it drops below 50% efficiency or something like that. That could be considered failure. It's really on you to decide what exactly failure looks like and what it means. Okay. So what does doing this look like? Well, we have a number of customers that have used our tools in order to do condition monitoring and predictive maintenance. And one that's very similar to the demo that we're going to be using today is a company called Safran Engine. They make jet engines, and they use this to make a condition monitoring system. So they use the sensor data coming off of their devices in order to be able to detect failure indicators and predict time to maintenance, all the things that we talked about. And what this leads to is improving the availability of the aircraft. Anybody that's flown before knows that it's not fun when your plane gets delayed due to mechanical issues. And this is really trying to minimize that sort of stuff. So if you don't have unexpected failures, things should depart on time. And if we're not doing a bunch of extra maintenance, it frees up work crews or maintenance techs to be able to make sure that things don't fail. So in addition to that, because you're only fixing the things that need to be fixed or maintaining things that need to be maintained, it reduces the overall cost of the operation of a given device or a given system. Now within this, there's kind of steps to this workflow. So you'd start on the desktop like we're doing today, doing some data analysis, doing some analytics, and essentially some machine learning or predictive maintenance in order to be able to predict failure. You can then take those models and push them out to where they need to be, whether we're compiling them to share with other teams and build out a more robust solution or integrating it with other platforms. Things like OCSoft or Pi servers for say taking the data in or deploying it out onto something like AWS or Azure for cloud deployment. And then moving all the way out to enterprise level integration where we are actually having this sort of system run in real time, integrated with our actual devices, being able to be viewed by the maintenance and service systems as well. Right. If you want to know more about this, there's a link down here where Safran did present it back in 2015. There's other ones as well. But so, like I said, we're going to be working with a data set that's very similar, or at least a similar idea to what we just talked about. So we're going to be working with the standard prognostics data set that comes from NASA, where we're going to take the sensor data from 100 engines of the same jet engine, and we're going to try to predict and fix failures before they arise. So at a high level, we're going to import the sensor data, we're going to train the model, we're going to deploy. Well, we're not going to do so much deployment today, but we're going to do a visualization to at least understand what it would look like when we're doing the deployment. Now, we talked about two different things, right? We talked about condition monitoring and we talked about remaining useful life estimation. And so we'll do both with this same data set. Now, when we're doing both of these, there's different modeling approaches we might take, and they'll fall somewhere along the spectrum of modeling dynamic systems. On the far left is first principles modeling. So this is probably the stuff you learned in your physics courses or your mechanics courses in high school and college. Writing a series of equations in order to understand how a system works. Okay, and that's okay for some more simple systems, but as things get more complex, we'll probably get driven at least somewhat farther to the right with data-driven modeling. And there are different techniques that fall along the spectrum, right? Physical models all the way on the left, machine learning / maybe deep learning all the way on the right, and then there's some sort of hybrid techniques, Kalman filters, system identification, more parametric models, things like that can also have their place in this. Now, the name of this presentation was Predictive Maintenance, a data-driven approach, so you might be able to guess which side of the spectrum we're going to be on today. We're going to be largely all the way on the right. We're going to be using machine learning techniques today in order to solve these problems. All right, so back to our problem. Our first scenario is we're going to do that condition monitoring, and this is pretty standard when we're looking to build out a remaining useful life system or any sort of predictive maintenance system. Starting with condition monitoring makes sense. It doesn't necessarily require us to have a huge bank of historical data. It lets us at least know the current state of our system and start understanding trends and how our system evolves over time, or if it does at all in a measurable way. And then once we have something like this, it can be fairly natural to start moving into kind of the second half of the remaining useful life estimation. So we'll start here because it's where we would start anyway. And in our particular scenario, we may or may not have failure data. Oftentimes these systems are designed not to fail, or we really don't want them to fail. So we may just not even have failure data available to us in the first place. So what can we do to deal with that? Right. This is often going to be used together with an existing maintenance scheme. Generally, it'll be scheduled, but you might have some sort of predictive system set up as well. Now, in this particular example, we're going to always be performing maintenance often enough so that there's no failures in our data set. Additionally, we do have some extra information from our maintenance crews telling us which engines could have ran for longer and which ones were in pretty dire need of maintenance when they came in. And so can we use this information along with the data that we have recorded from the sensors in order to be able to understand how we should schedule maintenance without even seeing a failure occur? Right, so that's what we're going to be doing first. Now, to do this, we are going to be using machine learning to solve this problem. We're doing this because this is a complex system. There's a lot of variables. It's too complex to know a governing equation, or it might take a lot of effort in order to be able to build one. And there's a lot of examples of machine learning. We'll see a couple today. But at a high level, machine learning is divided into two big buckets, right? Supervised learning and unsupervised learning. Now, with supervised learning, this is when we're actually building a predictive model, and we need both input and output data to build it. Unsupervised, we're really just looking at trends and trying to interpret and group our data and establish how it might evolve over time or space or whatever. Now, as I said, we don't have failure data, so we don't really have an output here. So we're going to be starting with unsupervised learning for our condition monitoring system. All right, so with that, let us hop into MATLAB and we'll get going. Okay, so I have the script that I had written before, and we're gonna walk through it to solve this problem. Okay, so first thing we're gonna do is we're gonna load in our data set. Now, our data is stored as a bunch of CSV files right now. I can open one of these outside of MATLAB, just take a quick look in Excel here, and just so we know what we're working with. So what we have here is we have basically different units, different times. Now in this particular data set, a time is a cycle. It's a flight up and down. Okay, and all of these measurements are essentially averages or some sort of statistical measure of these various sensors over that entire flight. Right, so we got our low pressure compressor outlet temperature, and so on. If you're not familiar with all these, it doesn't really matter. These are all just different columns or different sensor data that we're going to be using today to build our models. All right. Now, even though we're using cycles here, this time can be anything, right? So if you're measuring in hours or minutes or seconds or milliseconds, right? It's as long as you're consistent, any of those would work. All right. So coming back here, we're going to load in our data set. So let's load in one of these CSV files. So we're going to load it in for unit 1. This is the one we just looked at. And once we read this in, we're going to start doing some visualizations of it. Okay, so we load it in there, and we'll just look at a subset of the sensors here. So just kind of the first 9. Now, we're looking for a couple of things here. We're generally looking for some sort of trend to exist, right? So in this case, we can see this is going down, this is going up, 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 right? So a lot of these do have some sort of trend. Some of them are a little bit weaker, right? This top this top right and this bottom left, they go slightly down, but not as maybe strongly as some of those others do. And so this is telling us that there is at least some evolution of these sensors over time, right? They're going in some direction, which is good because we need them to go in some sort of direction. If we're looking to see how this behaves over time, if it just kind of stays stagnant, doesn't really move, or just kind of scatters sort of randomly, there's not much information we can pull from that. So this is a good sign that a lot of these do have some sort of trend associated with them. Now, some don't, and that's fine. We can always pull those out, or we can do different techniques in order to try to kind of mitigate those sensors that don't have as much information associated with them. Now, a really simplistic way that we might do this is say that we identify a particular sensor that we're interested in. So, say we take this one in, and we might do something like a control chart. So with a control chart, we'll have some sort of center to the data. We'll set a lower and upper control limit. And as soon as it goes out of that control limit for some amount of iterations, say 4 in this case, we'll say that it's not operating correctly. Now, this is okay for more simplistic systems, but there were a lot of sensor values in there. I think when I pulled it in, we had like 15 or 16 different ones. So we're throwing out 15/16 of our data if we're looking at just one particular sensor, which is kind of wasteful. And we're potentially missing out on some important interactions within the data by just looking at it in this very simplistic way. So we're going to take it kind of a step past this, but we're going to have a very similar idea, right? We want to be able to visualize and understand how the data is moving over time and be able to set these sorts of boundaries to say, within this boundary, it's operating correctly. Within this boundary, it's starting to deviate from normal behavior, and say even farther out of that, it's moving into failure. So similar idea, but we need to integrate the rest of the data that we actually have available to us. Okay, so the next step is we're not just gonna work with the one set of data. We're going to work with everything that we have. Okay, so to do this, I'm going to set up what's called a tall array. Now, the tall array is a data type in MATLAB that we can use for data that may be too big to fit into memory. It can also be used to be able to gather large collections of files or potentially databases, and it's constructed by first constructing a data store. Okay, so to construct a data store, I need to point it at where the data currently sits. So I'm pointing it at this data subfolder that I have. It's going to pull everything that's in this folder, which is just those CSV files, and essentially just concatenate them together to get started. Once I have the data store, I've kind of got 2 options. If the data in the data store is small enough to fit into memory all at one time, I can just call read all on the data store and just read it in as a normal MATLAB variable. At this point, I continue in the same way that I would using MATLAB, so nothing's really changed. I just use the data store to be able to easily collect everything together in one place. But if it's too big to fit into memory, or if I think it's going to grow to be too big to fit into memory, then I might create a tall array instead, right, which is this calling tall on the data store itself. Now, when I do this, it will create this tall table, and you can see the size of this thing. It is M by 16, so it's 16 columns and it's M rows. Now, M is just sort of a placeholder in this case. We don't actually know the number of rows, and it doesn't actually care. The tall array will work whether M is 100,000 or 100 million. It will handle, underneath the hood, what it needs to do in order to be able to deal with that. Now, once it's in the tall array, this is all my data collected in one place, and I can continue using it. Now, we're going to do one last sort of filtering here. I said that we're going to assume that we've always done maintenance on the system before it failure. Now, in the full data set we have, we actually do have time to failure, or the sensors all the way to failure. So we're going to sort of artificially limit it to make sure that the maintenance never actually happens, or sorry, the failure never actually happens, by only taking the first 125 flights for each one of these engines. Okay, now the data is too big to fit into memory and do any sort of visualizations on it. So what we're going to do is we're going to take a data sample of it. So this is just going to randomly sample 5,000 points from our overall data set. And then we're going to call gather to actually bring that in. So this is how you interact with tall arrays. You use whatever functions you use that are supported by tall arrays, and this will essentially queue up a set of things that are actually going to happen. And then when you want them to happen, you call this gather command to actually execute it. It will read through the data however many times it needs to, and then pull this into actual memory. So we would have sample plot in memory at this point. And we can create the same visualizations that we did for one engine up above, but now we're looking at all 100, or at least a subsample of that one, all 100. And we're going to look for the same things. We are going to look for trends, right? So we got a general downward trend here, down, up, up. This one, when I looked at it before, we didn't have really a trend, but we do have like an increase in variance, which can be helpful as well. So, we're still seeing some trends in this data at sort of a more macro level when we're looking at all of the engines that we have as opposed to just one, which is promising, right? We need that in order to be able to see any sort of evolution over time. Now, you may notice that these are on pretty different scales, right? Core speeds at around 9,000, fuel flow ratios are like 500. This is at like 40-ish, right? So if I were just to use this directly, core speed might outweigh everything else just by the sake of how it's being measured, right? Just being naturally larger. So the next thing that we're going to do before we move forward is we're just going to standardize our data. So a lot of machine learning techniques, including some data reduction techniques, which is what we're going to do next. We want to standardize so that we don't have sort of negative effects by having things in very different scales. So that's what we're doing here. We're just centering each signal on 0, and then we're just scaling it so that it has a range of -1 to +1, so everything's on even footing. Okay. Now, one of the issues we're having right now is that even though we're able to visualize individual sensors, we're not able to capture any sort of interactions between them right now, and getting an overall sense of how our system is behaving is still pretty difficult to visualize and understand, right? We're looking at 9 of the 14 sensors that we have, so we're still not even looking at everything. So in order to be able to both visualize as well as potentially model in the system, we want to do some dimensionality reduction here. We want to reduce our data set down to a fewer number of columns or fewer number of features, so that we're more able to visualize and understand what's going on. Now, there's a lot of different techniques that we can use to do this, but one of the most common and most popular ones, and the one we're going to be using today, is something called PCA, or Principal Component Analysis. Now, if you're not familiar with principal component analysis, the idea behind it is fairly simple. Say we have our data and it's being measured on a few different axes, right? They're measured based on however we're able to measure it with the sensors. Now, there's no actual guarantee that the spread of the data actually aligns with those axes. And so being able to understand the full extent of the information in its current state, potentially relies on a combination of these variables. So what we're going to do is we're going to rotate our axes so that they align with the spread of the data, right? So we have our first principal component is aligned with the widest variance or widest spread of the data. And then we'll keep adding more principal components that are orthogonal or 90 degrees off of all other existing principal components. And we can do this for all three, up to the number of original variables we have. But what this does for us is now we're able to, with this one principal component, be able to capture the widest variance of our data. And then the second widest variance of our data that is orthogonal to the first with the second one. And so we end up not needing to be able to, to use all of the original variables. We can use a subset and still be able to capture most of the information that's within our data. So using that idea on our data set that isn't 3, but it's 14 variables, we can do the same thing. So we call this principal component analysis function, and this plot is the amount of variance, or essentially the amount of information that we can explain in our data set with a given number of principal components. So orange is the amount that's explained by an individual component, and blue is the cumulative one. So we can see with just 2 principal components, we can explain about 88% of the information or the variance in our data set, okay? Which is a pretty significant reduction in dimensionality, right? We went from a 14-dimensional system down to a 2-dimensional system and still captured almost 90% of the information within. Right, so we're going to do 2 because that's really the, before the big drop off in the information. Now we get a few things from this, right? Because we're now down just to 2 principal components, it is now a whole lot easier to visualize our system, right? So this is our first 2 principal components plotted against each other. So this is what's called a bin scatter plot, essentially just a 2D histogram. And we can see that the biggest bulk of points is within this sort of area here. And then we've got 2 sort of tendrils reaching out to the right and to the upper right. Now, just for a quick check, let's look at what our higher principal components look like. So this is the 3rd versus the 4th. And we can see here it's zero-centered with a sort of normal distribution around it, right? If I was maybe looking at this from the side, it would probably look like this, right? So very standard normal distribution. And this is what I would expect from just noise, right? So this is just kind of confirming that there's not really any information contained within these higher principal components. Now, one of the nice things is that we can actually take a look and see which of our original signals contributed the most to the principal components that we're using. I said before, this is just a rotation, right? So every principal component is just a linear combination of our original variables to generate them. And we can see our first principal component, everything is at least in the same order of magnitude in terms of how much it contributed. We're looking really just at the magnitude here. So positive or negative doesn't matter so much. So everything is, point something. When we get to the second principal component, we can see that some of them are starting to drop off a bit, right? Some of these are starting to reduce in magnitude by some. The core speed seems to be particularly important here, as well as the physical core speed. So those might be more data rich than the others, which is potentially surprising since I called them out for not having strong trends earlier. But according to this, at least they are important. Right? So that is principal component analysis. And that's just one technique for dimensionality reduction, but I would say it is probably the most common. And so let's continue in using this idea. All right, so we're going to take a sample of our PCA score for plotting, just like we did before. And we're gonna use that idea that we talked about before, right? We want to be able to build some sort of warning system where we're able to define boundaries between normal operating, questionable operating, and close to failure operating. And so let's take a look at our data in order to try to see if we can establish that. So for this first visualization, and this is in the principal component space, right? So first principal component versus second principal component, we'll plot our first and last points. So the first points are the blue over here. And we can see they're in that sort of dense rectangular section we saw before. And, they're all starting over there. The last points has a much wider spread. We're seeing some of them start to, go out to the side and up and to the side. So there is some movement and some sort of spreading out as operation happens, which is good. That's what we want. We want to see these sorts of movements or these behaviors, because now we can start looking at maybe drawing boundaries. But we can also see that there's this sort of overlap, right, where there are still quite a few of these red points that are within this original starting region. And these are likely the engines that didn't need to be brought down for maintenance so quickly. So we're seeing that if we just did a scheduled maintenance at 125 cycles, maybe a half or two-fifths or like a half of our engines are being brought down earlier than they need to be. Now, I said before that we had talked to our maintenance crews. They were able to tell us which engines needed maintenance and which ones didn't, and they identified a few specific ones that are particularly bad. So let's highlight those in our same visualization. And we're just highlighting the last 10 cycles of our most problematic engines. So we can see here, 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 here. And it works out nicely that the most problematic ones are the ones that are farthest away from our sort of dense starting point that we have over here. So this is good, right? It means that we have sort of an area where normal operation, or at least starting operation, occurs. It seems the worse it is, the farther it is. And potentially there might be some path that can be tracked, from here to here. And so, if we scroll farther down, we can track this sort of path. So this is one particular engine. This is one of the particularly bad ones. And if we trace this path back, we can see that, it had a, once it started really degrading, it shot out to the right, but, kind of had this sort of meandering path through this point to start with. So it did spend a fair amount of its time in the sort of normal operation still. Okay, so with this, we now have some understanding of our system, right? We've got that nice dense starting point, and as things degrade or as things age, they push farther and farther from that point in sort of two ways, right? Directly to the right or to the upper right. So we'll use that in order to start establishing some criteria for when we're going to say it's moving out of normal operation. So we'll choose these boundaries. These are fairly arbitrary. I mean, there's some statistical reasoning behind the boundaries that we chose. We chose that 90.5% of the data falls within green, and then 99.5% of the data falls within green and orange, or green and yellow, whatever color you want to call that. And then the last 0.5 are out in this red. So now we have these boundaries and this way to transform our data into this set. At this point, we could take sensor data and we could say, take the data, convert it into the principal component, and let's say that the point falls within here, right? We calculate it and it falls there. Well, we now know that the system is in a warning region, right? It doesn't necessarily need to be brought down for maintenance yet, but we should keep our eye on it and be ready for when it's going to be. Or if we're being more conservative, maybe we bring things down for maintenance once they're spent some time in the orange, right? Say they spend 5 cycles in orange in a row, then we bring it down for maintenance then, right? It kind of depends on how conservative or aggressive you want to be in your maintenance schemes. All right, so I'm gonna take a second. I'm gonna look and see if there are any questions in the chat. Looks like no. Remember, if you do have any questions, feel free to ask them in the chat. If you want to ask them in English, I can answer them. If you want to answer them in Portuguese, we do have somebody from OpenCAD who can answer in Portuguese as well. All right, so, oh, I think I see, oh, or not, maybe not. Okay.
Hello, James.
Yep.
So far, no question, but if somebody later sends us any question, then we can maybe send you, and we bring back for them. Okay.
Okay. Yeah, and I can see the chat window as well. So.
Yeah. Okay. Thanks.
Yep, no problem. Okay, so, you know, one idea you might have on this now is we have these boundaries, right? And with these boundaries, we now have labels associated with each one of these points. If we have labels, that means we have an output, which, if we come back here, means we now have supervised learning available to us as a potential option. So we're not going to do this today, but when you receive the content for this webinar, there is another script in here called the classification script, and that goes through using the labels we just generated from that in order to build a classification model so that we can actually make a prediction on that sensor data of whether it has a short, medium, or long time until failure. Like I said, we don't really have time to go into this today, but if you're interested in taking sort of the next step of what we did here into building an actual predictive model, or I guess this would be more of a prescriptive model because it's just telling you what the current state is, then that's where I would suggest looking this classification script. All right, but with the time we have left, I do want to spend some time with our second example. But before we do that, let's wrap up what we did here and what we might do with the information we now have. Okay. So our current system, right? Before we have the condition monitoring system is 125 flights. We take it down no matter what. But now that we have a condition monitoring system, whether it be the unsupervised we have now, or that classification one I mentioned, instead, what we can do is say, okay, we have this in place. Let's start testing it. We are at 125 flights. Let's push it out to say 135 flights, and if it spends 3 flights in a row in yellow, then we'll bring it down for maintenance early. Otherwise, we'll bring it down at 135. And you do that, and you say, oh, well, only a third of our engines are being brought down from our system, so we can probably be a bit more aggressive on this. So let's say maybe 150. And now, say 2/3 of our engines are now being brought down for maintenance through our condition monitoring system rather than just a scheduled maintenance. And you can keep pushing that out until eventually everything is done by that, once you have more data and more faith in the model and more understanding. Or, you potentially just you're capped at some amount through some sort of regulations, but at least it lets you get up to that amount with some confidence and minimizing any failures that would have happened if you had just gone all the way out to that amount in the first place. So another example of this being used, this is a paper and packaging manufacturer named Mondi. They used our tools in order to build a system very similar to what we just did. If you look at the picture down in the corner, you can see a visualization that's kind of very similar looking, where they're able to take sensor data off their systems. This is for manufacturing devices, and reduce the machine downtime of those systems because they're able to know when they're going to fail or when they're getting closer to failure, and as such plan accordingly. If you want to learn more, there's a link to a user story here as well as the results from this implementing this system. They also built out a visualization tool in MATLAB in order to be able to look at the sensor data and understand the current state of the system, directly from this rather than looking at code or something like that. Okay, so let us look at our data set again, right? This is the turbofan engine. We're going to look at it slightly differently this time. So we're pulling in we're pulling in another 100 engines. So we're doing 200 engines this time instead of 100. And we're going to be looking to actually build a predictive model. We're going to forecast the remaining useful life of our system. Now, when we do this, we're going to have some combination of sensor data from our equipment, known failure thresholds, and or runtime to failure of similar equipment. Okay. We're actually going to use condition monitoring to determine when the system starts degrading. So we would still be using that model we built before. And then once it starts degrading, then we would use our remaining useful life estimator in order to predict how much longer we have until our system is going to be run off for failure, right? So condition monitoring tells us the current state, and then our remaining useful life tells us how long we have until failure is actually going to occur. So looking back at this, because we have input and output data, because we know how long until things fail, we're going to be in the supervised approach. And because we're looking for a specific number, we're actually going to be using a regression model specifically. Now, there's a number of different remaining useful life methods that are available in the predictive maintenance tools in MATLAB. And the way we choose which one to use is based on the data we have available to us. Okay, so say we have a system or a device and it's going to start in an ideal state. It's either brand new or just got brought down for maintenance and it's in some ideal state. It's going to run for some amount of time, it's the lifetime, and then it will fail, whatever failure means. Now we have different opportunities to capture data in this, in this life cycle. Say we have no sensors at all. Instead, we know how long the system lasted, and we might have some operating conditions or things of that nature, but no sensor data. Now we can still work with this as long as we have a sufficient number of devices that have run. And if we just have that lifetime data, we would use something called survival methods. Now, say that we have some data, right? We were able to bring sensors in occasionally or just gathered it in certain segments of its operation, but we know some things about what failure looks like. Or we have some sort of failure threshold that we can define, then we can use something called degradation methods. And then the sort of purely data-driven approaches, say we actually have sensors on this thing from life till death, right, until from start till finish. So that's called run to failure data. Now, if we have that, we don't actually need to know what failure looks like or have to define some sort of failure threshold. We can rely on the data on its own and use something called similarity methods, and that's actually what we'll use in the demo. We have that sort of run to failure data. This is the same thing I was talking about, just broken out a little bit more detail. Within these different models, there are variants of that model that you would use based on specific characteristics of the problem. In this particular case, we do have some known degradation dynamics. We know how this degrades over time by whether it's linearly or exponentially or quadratically or so on, that sort of dynamics. And so we'll use this residual similarity model because of it. If you want some more information on this sort of model selection, there's a whole bunch in the documentation about this. You'll see this visualization again with some more explanation. Okay, so let's hop back into MATLAB and we will walk through this problem. All right, so I'm going to load my data set in, and we're going to do some very similar stuff, right? We're going to do some trendability analysis. This is the same thing we did visually. This is just being done sort of numerically, where we're trying to pull out the sensors that have the most change over time. So this is essentially just sort of fitting the data to this linear degradation model, and we're going to pull out the slope and just pick the ones with the highest slope, so the most change over time. It ends up being these three things: the low pressure turbine outlet temperature, the static high pressure compressor outlet pressure, and the bypass ratio. And this is just a subset of 10 of the engines that, this is the sensor data for those 10 engines. Now, once we have the sensor values that we're going to keep, right? This is our dimensionality reduction, right? We did PCA before. This one, we're just choosing a subset that have the most change over time. But once we have that, we're going to create what's called an ideal health indicator. This is the value that we're going to use to determine the current health of the system. Now, we're going to eventually use these sensor values to estimate what that might be, but first we're going to create what it should be or what we think it would be in an ideal state. And in our case, we create something that looks like this. We are going to assume that it starts at the ideal health at 1, and it will degrade linearly down to 0, where it will fail at the time that it failed, right? So these different engines that we have, they failed at different times, so we have sort of these different sloped lines going down. Okay, so that's our ideal health indicator. Now, we're going to use the sensor values that we pulled out in order to estimate this ideal health indicator. And so this is just a pretty simple regression. Excuse me. Where we're just going to do a linear regression or linear fit, where the X values, the inputs, these are the sensors, and the Y, that's the ideal health indicator. And in predictive maintenance, this is called sensor fusion, or creating a fused health indicator. If you're like me and you come from the land of Kalman filters and controls, sensor fusion means something else, but they use the same term here. So we're fusing our sensor data together to create this fused health indicator. And so if we take a look, this is what the fused health indicator looks like. So it starts at 1, which we're kind of assuming, and then it degrades in some structure, right? This isn't linear, but that's fine. And they don't actually ever go to 0, but that's also fine. But we now have these time series of our health indicator of our specific engines based on the sensor data itself. And we would do this for all 200 of our engines. This is showing the first 10. All right, so let's take the health indicators, and we're actually going to build our remaining useful life estimator at this point. So to do this, we're going to use that residual similarity model, and this works in a very similar way as K nearest neighbors does. If you're familiar with that model, if you're not, essentially what it does is it takes a bunch of points and it will compare it a new point to the closest K neighbors. In this case, we're setting that to be 50. Now, we're not looking at points, we're looking at time series in this case. So we're comparing it to the closest 50 time series from our original data. Now, as you might imagine, storing a bunch of time series directly in a model would make it very heavy and clunky to work with. So we're actually storing an approximation of each of those time series. So in this case, it's a second ordered polynomial approximation of each of the time series. All right, so we'll create that. We can fit the model and test to see how it performs. But I'm going to run. I've not actually been running these things, so let me run these and we'll do it. So come back up here, run this, so we get the number of samples. We'll do all the things we talked about already. So we'll create the ideal health indicator. We'll create the fused health indicator. It's just a good review, I guess, of everything we've done so far. We don't need to do the visualization, and then we'll build our model from those fused health indicators. Okay, so now that we have our model, we're just going to do the same pre-processing that we did on the data set we used to train the model for our test data set. So this is just kind of pulling out the specific values we care about and computing the fused health indicators for our test set. And once we have that, we can use that in order to test to see how our model operates. So let's do that. So we have an animation here that is going to come up in a second. And it will allow us to visualize the performance of our model over the operation of a system. Okay, so Normally, we wouldn't start doing this until our condition monitoring system is telling us we're starting to degrade. And the reason for this is that we just don't have much, but we're gonna start from the start here. And up in the top right, you can see this red line that's growing. This is the the time series of our test engine as it moves along. Now, the left one here, this is the actual estimation. This is the estimation of how long we have until it fails, along with some confidence intervals for it. So the green is the actual value of how long it has until it fails. Red is the estimated, and we can see that we're starting to converge now as that as we have more of the time series being populated. The bottom one here, this is just the histogram of the 50 nearest time series and when they would fail, and then just a fit to make the actual estimation. And at this point, we can see that we're starting to converge. We're actually very close to the actual value. And we can see that it's around 60 cycles before failure that we have an accurate estimate, right? And this 60 cycles before failure, this is potentially when it would start getting into the warning, warning range in our condition monitoring systems. It's probably where we'd start to begin with. But we can see we get pretty ample warning for when it's going to fail. So we have a long time to act on it before failure. Right. So this is an example where it worked quite well. Let me close this real quick and we'll run it again. This time with a new engine. And this engine is actually an example of when this particular model doesn't work as well. We don't see it immediately, but we can see that it is severely under-predicting right now. It's saying that it's going to fail a lot earlier than it actually will fail. If we let this evolve over time, we would see that there is sort of a cusp of when it it kind of bounces back up for a bit on its fused health indicator and goes outside of the range of the data we have. And that's kind of one of the limitations of this, is that you really only know what you know, or you know what you've seen before, right? And so you're pretty reliant on the data that you have in the model. But what that also means is, as you get more data, as this model is used more, or as you record more information, your models will just naturally improve by having more data available to them. So we can see it's kind of doing that bounce back now. We can see that it's the nearest time series are shifting to try to match it as best it can, but it will never actually converge until pretty close to failure, because it ends up going outside the sort of range of time series that we have. Right. So I'm gonna stop this just in the interest of time, but that's that one. Right. So that's a remaining useful life model. We can see that it works quite well in some cases, and in other cases where we don't have the full data yet, right, there are some limitations to it, but these models will, as I said, improve as you gain more and more information and data for your system. Now, it's not enough to just build these in MATLAB. You do want to be able to integrate them where they're needed. So, with MATLAB, we've got a variety of deployment tools to allow you to deploy these models where they're needed. If you're looking to deploy out onto, say, the cloud, then you can use our compiler tools in order to compile either as like a standalone executable, web application, or a variety of different software libraries to integrate with a, potentially a different front end. And then if you want to deploy just the algorithm, say to like an edge device or a microcontroller, then we do have code generation tools available as well to target embedded hardware for some of the models we talked about today. These are MathWorks services. I'm sure OpenCAD has some similar things that maybe they want to talk about the specifics on that. But the training is available as well for learning more about the predictive maintenance tools in MATLAB. And then a few key takeaways, right? So we talked about two different facets of predictive maintenance today. We talked about remaining useful life estimation and condition monitoring. The one we didn't talk about is fault detection and classification, where that's the why did it fail. And in the same tools, the predictive maintenance toolbox, there are models and tools for that. We just didn't have the time today to talk about that particular one. But with what we did talk about, right? Predictive maintenance and unexpected, especially behaviors, are potentially very expensive or risky, and so we want you as engineers and data science to be able to build out models to help prevent those sorts of situations. Lets you save money, increase reliability, as well as just preventing risk as well. All right, so that's all I have for you today. If you do have any other questions, feel free to ask. I don't think I see any in the chat. Sylvia, I don't know if you had anything else you wanted to say.
No, I think there is no question in the chat, nor in the question board as well. Okay. But if someone has any doubt, you can email us, OpenCAD, and we can try to answer, or sending those questions to James. Okay.
All right. All right. Well, thank you for attending.
Thank you, everybody. Thank you, James.